All right, for us, the most convenient way of expressing the composition of a solution is by molarity. But molarities aren't normally shown on ingredient bottles. What's normally shown is percent composition by mass. And so that's what they want here, the percentage acetic acid by mass. And so you have to figure out how many grams of acetic acid, how many grams of solution, pure acetic acid versus acetic acid solution, and then times it by 100%. You'll need some additional information for this calculation, so take a look at what they say here in the procedure. There's a piece of information that's missing here, when you do this particular calculation. See if they say something in the procedure that gives you that piece of information. All right, so yeah, you'll need to do that. Officially this is due, but on exam weeks I don't want a whole bunch of stuff due, so you can turn this in next week. I forgot to put the upload link for the chemical reactions. You can upload just a PDF of your lab notebook or something, or just rewrite the equations. That would be good too. All right, other questions? No other questions? Then we'll get started with experiment 8. This particular structure, so what they have here is formic acid, and they draw the Lewis structure here. The Lewis structure doesn't have to be an accurate representation of the actual structure, but what we're going to do is we're going to make a more accurate representation of this. So this particular drawing of formic acid I don't really like that much, and so we're going to redraw this one. The first thing is we need the Lewis structure. Once we get the Lewis structure, then we count how many groups. So how many groups of electrons around this carbon here? 3. Double bond and 2 single bonds. And so what type of electron group geometry does this adopt? Yeah, trigonal planar. And so we look at the carbon here, and that's what they're doing. They're counting the electron groups here. That's 3, and out of the 3, we have 3 bonding groups, 0 lone pairs. Out of the 3 bonding groups, 2 of those bonding groups are single bonds. 1 of them is a double bond. And so we expect the electron geometry around carbon to be trigonal planar. Okay, then when we look at the molecular geometry, so we have the electron geometry here, which is trigonal planar. The ideal angle for trigonal planar is 120. And so that's what they're asking for here, just the ideal angle. Now, we're going to figure out the electron geometry first, and then after the electron geometry, we figure out the molecular geometry. The molecular geometry is the geometry of the bonded atoms. So when we look at the bonded atoms here, what is the geometry of the bonded atoms? Trigonal planar also. And so that's what they have here. It's trigonal planar around the carbon. And it's trigonal planar electron geometry as well. The ideal angle is 120 degrees. All right, then what we're going to do is we're going to take a look at the oxygen next. And so when we look at the oxygen, how many groups of electrons around this? Now we have two oxygens. We have what we call a blank oxygen here, and we have a blank oxygen here. What were the terms I used for describing these two oxygens? No, I mean, to describe the two different oxygens, I used a word. I don't know if you remember. You didn't catch it. But just saying, did anybody catch what I called this type of oxygen versus what I called this type of oxygen? No. I called this bottom oxygen here a bridging oxygen because it's bridging these two atoms here. A bridging oxygen is central. And then I called this top oxygen a terminal oxygen because it terminates the link. And so we have a terminal oxygen and a bridging oxygen. Let's take a look at the bridging oxygen. That's what we're looking at here. We're looking at the bridging oxygen. How many groups of electrons around this bridging oxygen? No. 4. There are 4 groups. Out of the 4 groups here, we have 2 that are bonds and 2 that are lone pairs. And that gives us a total of 4 groups. When we have 4 groups, what's electron group geometry for this? It is the electron group geometry for 4 groups of electrons. Tetrahedral. Good. Tetrahedral. And that's what we have here. Now, there are multiple ways of drawing tetrahedral. When we draw a tetrahedral, we want 2 groups in the plane at all times. Normally, when we draw tetrahedral, the 2 groups that are in the plane, I draw 1 group on the top and 1 group coming down at a 109 angle. So these are in the plane. And then I'll draw 1 group that wedges out like this, and then 1 group that goes in. These balloons represent the groups. And so that's the dashed in group. If I use what we call a wedge dash diagram, it's going to look like this. These are just normal lines, meaning they're in the plane. This is going to wedge out, meaning it's coming out of the plane. This is going to dash in, which means it's going in. Do you see that visually? Can you see that? All right, to help us better see this, what we're going to do is we're going to use model kits. And so what I want you to do is I want you to go check out a model kit from the stock room right now. And so let me pause this. All right, the blue ball should have 4 holes. Do you see that? All right, then put in, we're going to put in, let's put in like 4 sticks, either short or long, into the blue one. Actually, put either 4 shorts or 2 shorts and 2 longs. Yes, it is. All right. Now what we're going to do is we're going to make a tetrahedral type geometry. So take the blue ball and then with the 4 sticks, do you see this arrangement here? So twist it so that you can see it. You're going to put 2 in the plane, so make an imaginary plane, and then 1 sticks out and down, 1 sticks out and back. Do you see that? So the orientation that you're drawing it in. So orient your model so that it looks like this, and then draw it. You come up with the same drawing? In other words, when you do this, do you have the wedge oriented down and the dash oriented up like this, or do you have it opposite, the wedge going up and the dash coming down? How does it look to you? All right, now what we're going to do is we're going to rotate this and draw it in a different orientation. We're going to draw it like this. You're going to put the 2 bonds that are in the plane up like this. And what that means is that we're going to have a wedge coming out like this and a dash going in like this. Could you orient it like that? So just twist it. In other words, just rotate it a little bit so that we get this orientation. Do you see that? Yeah? Yes. Okay. So this is tetrahedral. In tetrahedral, there are 2 in the plane, 1 coming out. And so when we draw the tetrahedral, we put 2 in plane, and then 1 out, 1 in. All right, so what I want to do is I want to modify this drawing here. What we're going to do is we're going to put 2 in the plane. So this is going to be our 2 in the plane here. And that means the lone pairs are not going to be in the plane. That is, 1 lone pair is going to wedge out, and the other lone pair is going to dash in like this. So I'm going to show that a little differently here, and I want to redraw this. And so the trigonal planar is fine. But the tetrahedral, I would like it changed a little bit. Let's see, is this working? So the tetrahedral, we're going to draw 2 in the plane. So these are the 2 bonds that are going to be in the plane of the board. And then 1 lone pair I'm going to wedge out. The lone pair that I'm going to wedge out, I'm going to fill solid like this. And then 1 lone pair is going to dash in. And so I'll draw it like this. And so attached to the blue one, on one of the sticks, attach a black. The black is going to represent the carbon. And then attach a white. That's going to represent the hydrogen. And then orient it, twist it so that these 2 that are in the plane point upwards, and the 2 lone pairs point downwards, and see what the orientation of the lone pairs are. Do you see that? What I'm trying to draw here? Can you visualize that and see it in the model?
Is it a black carbon or is it blue carbon?
Black is carbon. I'm going to use blue for oxygen. Normally red is oxygen, but our reds don't have 4 holes. So I'm using blue for oxygen. Do you see it? Yes?
You said 1 black, 1 white.
1 black and 1 white.
Is the black one attached to the long one or the short one?
The short ones are going to be the lone pairs. The long ones are going to be the bonds.
Just like this.
Yes, like that. And then look at the short ones. The short ones should be the lone pairs because the lone pairs are being pulled in a one-way tug of war, whereas the bonds are being pulled in a two-way tug of war. Do you guys see it? Yes? All right. Next, what we're going to do is we're going to put the carbon. Now, the carbon's not going to be perfect because we don't have the appropriate ones. But what we're going to do is we're going to put two long sticks or three long sticks. You could do 3 long sticks. It's fine. I do 3 more long sticks to the black. And then 2 of those long sticks attached to a blue.
So the black one would be on the top?
All right, so we did ammonia here, which is trigonal pyramidal. So build this. Nitrogen's blue. Use a short stick for the lone pair and long sticks for the single bonds. And then take a look and see if the bond dipoles cancel or not, and tell me if it's polar or non-polar. And this was the previous, since I forgot to record it. The bond dipoles don't cancel here. And this is what's keeping this hydrogen up here. Hydrogen bonding interaction. You get it? Do the bond dipoles cancel or they don't cancel? They don't cancel. And so the molecular dipole is going to point straight up. So if these 3 are pushing it up, then the molecular dipole is the sum of those 3, and it's going to look like this. It's going to go straight up. And so we have a molecular dipole that points straight up like this. And so we say it's polar. All right, so what you're going to do is you're just going to continue this for the rest of them here. And then you're going to build the models, and then I'm going to check it off. I'm going to check off your drawing to make sure your drawing is accurate. The other thing we're going to do today is we're going to go back and take a look at this experiment. Do you remember this graph here? Yeah. What we're going to do is you graph this by hand. And I checked those. But some graphs are way off, you know, and it's easy to be way off here because the data points are kind of close, so just a slight tilt in the angle could make the intercept way off. So what we're going to do is we're going to do this. You're going to take your data and you're going to plot it on the computer using Excel. And so how many people have never used Excel? Okay. Yeah, Google Sheets is fine. Everybody's used Google Sheets. This is pretty much the same thing. We have Excel here, so we're going to use Excel. And so let's say I'm going to make a plot of some data. And so this would be the Charles Law experiment. And the data that we took, had two trials. We had trial 1, and we took some temperature in degrees C. Oops. And we took the volume. And so we had like 100, and the volume was, let's say, 453. The volume is in milliliters, so I should put that in here. I'm just going through. We're gonna go through it together over there, and then we cooled it down to, let's say, about 31. Actually, this we need more decimal places. We'll go 31.2. And let's say the volume shrank to 341 milliliters. All right, so what we're going to do is we're going to plot this data out. And so what I can do is I can select the headings and the data, or just the data itself. Let's go ahead and select the headings and the data. And then what I'm going to do is I'm going to insert a chart here. This is what we do in Excel. And I'm going to insert a scatter chart like this. So we have the data here. Actually, I'm going to just select the data. So I have this scatter chart here. And then what I'm going to do is I'm going to fit this to a line here. But the way we do it in Excel is we do add trend line. And then I wanted a linear trend line like this. And then I'm going to ask Excel to tell me the equation for that line like this. And then I'm going to forecast this. I'm going to forecast this backwards. Maybe I'll forecast this backwards 300 periods. That's probably too much. I'll forecast it backwards 200 units. Maybe I'll forecast it backwards 150 units like this. So what I'm looking for is I'm looking for where it intercepts the x-axis here. And that's going to tell me that. So it looks like it's intercepting here. But what I'm going to do is I'm going to use this equation to calculate the intercept. So I'm going to set y equal to 0 and then solve this equation for x. And then I'll get the intercept here using Excel. So we're going to do that. I did that for your plots, and I got the intercept if you had calculated it using Excel.
Do you have these Excel directions written down anywhere so we don't get lost?
No, I don't. I don't have the Excel definitions. That's why when we go in the computer lab, we'll do it together, step by step. So I'm going to hand back your experiment 3 later today, and then we'll go back in and do it by Excel. Okay? You can see how well your hand plot came out. All right, so just to work on those. Try to finish it. Try not to waste too much time on this particular one because we only have 1 day for this, plus we're doing the Excel. And so try to build the models quickly and then draw and then bring it up. I'll check it off.